Hey guys, welcome to my channel, Math for Teens. In today's video, we'll be deriving the formula for integration by parts. Now, the prerequisites you're going to need is the product rule of differentiation and the fundamental theorem of calculus. And I'll explain the latter because I think it might be a little bit more mysterious for some of you. So, really all you need to know about integrals for this video, although if you're using integration by parts, you should know more about integrals than just this. But what's essential is that an integral, also called an antiderivative, asks the question, given a derivative, let's say whatever we put inside our integral, our integrand, let's say our integrand is a derivative, your integral will output the original function. It essentially undoes your derivative. So if I have, the integral of x squared, I want to know, I'm supposing x squared is a derivative. And I'm going to ask you now, what would have been the original function if this is its derivative? And so you would essentially do the opposite of the power rule. And instead of subtracting one, you would add one to your exponent. And you would have x cubed, except if you differentiated this, you'd have 3x squared. So to cancel the 3 that would come over here, you put 1 on 3. So now when you use your power rule, this becomes x squared. Okay, so this notion of antiderivative should tell you that if I take an integral of a derivative, then the original function, the function whose derivative is this, and the output of our integral is just f of x. So this is all you really need to know for now. And in the actual fundamental theorem of calculus, they take a definite integral, so along a certain bound or domain, and then it would become f of the upper bound, your domain, so f of b, minus the lower bound, so f of a. That would be your true fundamental theorem of calculus. But all you need to know is that taking the integral of a derivative just undoes the derivative and it goes right back to being your original function. And without further ado, let's get into integration by parts. So this first step is just your product rule of differentiation. So let's say that a is equal to a of x, so it's a function of x. Just the lighting for you guys. Yeah. And let's say that b is also a function of x. Now, if I want to take the derivative of the product of these two functions, sorry, some lighting issues. The product rule tells us that this derivative will be equal to a prime, so the derivative of a times b, plus a times the derivative of b. And now we integrate. So now I say, okay, now I want to take the integral of this derivative. Okay, I'll take the integral. What you do on one side, you do on both sides. Taking the integral of this to this derivative is analogous to taking the integral of all of this. So I'm just going to rewrite it so I can do it cleanly. It's analogous to taking integral. We also have to say along what axis we're integrating. We're integrating along x, so we have dx. So this is analogous to taking the integral of a prime times b plus a b prime dx. Okay, I think that my marker might be running out, so let me quickly. Okay. Now, just like the derivative of a sum is a sum of derivatives, the integral of a sum is just the sum of integrals. So this is just the same thing as the integral of our first term plus the integral of our second term. So this will just be the same thing as integral of a prime b dx plus integral of a b prime dx. And from here, the rest is just changing notation so it can look like your integration by parts formula looks like. So So the first thing we did was the fundamental theorem of calculus, and it told us that an integral undoes the derivative, so these two cancel. You just return to your original function. So now we have AB. That's all we have left. Okay, on this side, this is where we're going to do a little bit of a change of notation. And we're going to make a comparison between the Newtonian and Leibniz's notation for derivatives. So we have on one side a prime, and this is the same as saying dA over dx. The two are equal. Okay, well now that means that if I multiply both sides by dx, I get a prime times dx is equal to dA. Okay, this is interesting, but why did I do this? Well, you might notice in our equation, we have a prime dx. And yes, you can sub that with dA. So this simply becomes b dA. So it's the integral of b dA. And likewise, b prime is the same as dB over dx. Multiplying both sides by dx, we get b prime dx is equal to dA. And look over here, we have b prime dx. So we're going to sub that with dA. So this entire integral becomes dB. We'll replace it with dB. Okay, so this entire integral becomes a dB. Wow, my letters are being mixed up. All right. And if I just rewrite this cleanly at the bottom, this is what you know as your integration by parts formula. Yeah, AB is equal to integral of b dA plus the integral of a dB.